Yeah, okay, so now we begin with a session that stands in between you and the lunch. So the first speaker of this session is Professor Arnab Sen from the Indian Association for the Cultivation of Science in Kolkata. And he'll tell us about understanding disorder-induced phases in dipolar spin ice.
Okay, so thanks, Yasser. So I'll talk about this particular problem where we'll try to theoretically understand what happens if you disorder a particular spin liquid. And we'll see that there are certain interesting phases that get generated due to this. And it'll also tie up with some of the slides we saw in the experimental overview talks and also in Jason's talk today, in the sense that there would be phases which show both certain liquid degrees of freedom and certain glassy degrees of freedom. But because this is theoretical, we'll be able to identify all that's happening, unlike the experiments. Okay. Good. So before I start, I would like to thank my collaborators in this work. So basically, I had done some previous work with Roderick Meusner on this, which is already published. And then we were trying to understand certain low temperature phases for which we required to actually build a new cluster algorithm for studying certain spin glasses. So that's basically Tushar Kanti Bose's work, building this cluster algorithm. And he also has a poster here. So I would actually explain also towards the end of my talk his work. But if you have any further questions, you should please ask him, because after all, this is his algorithm. Okay? And I would also refer to some previous work which I did with Shivaji Sondhi and Wojciech Kaiser during the course of this talk. Okay, so I'll rush through the introductory slides because after the tutorials, all of us are experts in frustrated magnets. So this slide was also shown in the tutorial. So basically, we can ask the perverse question of what's a spin liquid. So, yeah. Thanks. Okay, so this terminology can be thought of like this. So by correlating it with the solid, liquid, and gaseous phases of normal matter. So a spin solid may be thought of as an ordered phase, which actually breaks some spontaneous symmetry. So a ferromagnet or an antiferromagnet is an example of that. And we already saw that that actually leads to very well-formed excitations, which one can probe using inelastic neutron scattering. And these are these spin waves. And this is the experimental data, which was already flashed during the tutorials. Okay, so that's a spin solid, if you wish. A spin gas, on the other hand, is some quite uncorrelated phase of matter, where each spin may be doing its own fluctuations totally independent of the others. And that's like a totally uncorrelated paramagnet. So that's a spin gas. Whereas one loose definition of a spin liquid might be that it's neither this nor this, but it's something in between. So it's some very strongly correlated paramagnet which hasn't broken any long-range symmetries, but it's very strongly correlated, so it's rather different from this phase. Okay, so this is, of course, a bit of a loose definition. Yeah, I mean that it's imprecise, yes. Yeah, some people put it for emphasis, yes. Okay, so again, during the tutorials, we heard some slightly more precise definitions. So one way of thinking about it may be that these are low temperature phases, magnetic phases, which actually break no symmetries of the underlying Hamiltonian, and therefore it's not at all straightforward to write any local order parameter here. But nonetheless, the non-triviality can be seen by noticing that the excitations in these phases are completely different from conventional ordered or disordered states. And This was an example which Avinash already showed in his talk. So basically, if you just take the 1D Heisenberg spin chain, for example, then instead of Magnon-like excitations, which are what you would get if you study something like an antiferromagnet, so instead of a Magnon-like excitation which carries spin 1, you would get actually fractionalized excitations which carry half of that spin quantum number. And in 1D, we basically understand how that happens very well. And there's, in fact, a full Bethe-Ansatz solution for even the S of Q comma omega. And one can actually even see that in experiments very nicely. And of course, they both agree. But even in 1D, the fact that spin-ons exist, of course, one can sort of argue that there are fractionalized excitations which may give rise to this continuum, but the sharp argument that spin-on exists, of course, only comes from the Bethe-Ansatz solution. Okay, right. So in 2D and in 3D, we now know many theoretical examples where we can cleanly show that quantum spin liquids exist. But unfortunately, in experiments, we haven't yet found any smoking gun signatures of fractionalization. But in this talk, I would actually focus on classical models, where this spin is a classical object. And actually, we'll see that even these classical models can present very interesting instances of liquidity and fractionalization at low temperatures. And of course, experimentally, these are also of relevance, because imagine that your spin quantum number is maybe 3/2 or something higher. Then unless you are at some very low temperature, this classical modeling of the spin system actually even works quantitatively. Okay, right. So, of course, this is again something which we saw in the tutorials. So you might ask, what's the weak diagnostics for a spin liquid, or something which might have a tendency to a spin liquid at least at some finite temperature? So then, as was pointed out in several talks, one may look at the magnetic susceptibility, and of course at high temperature, like any other magnetic system, it follows the Curie-Weiss law, from which you can extrapolate what the Curie-Weiss temperature scale is. But unlike other systems, even if you go far below the Curie-Weiss temperature, you still see no tendency of ordering. And ultimately, for most experimental situations, if you go to a rather low temperature scale, something unusual happens. And in fact, we saw instances that that unusual thing may even be a spin glass, but it's a rather weird kind of a spin glass, because there seem to be both fluctuating degrees of freedom and very slow degrees of freedom. Right? So in this talk, we'll try to understand what happens to the dipolar spin-ice model when we introduce disorder here. And therefore, I'll comment on this here, and I'll also comment on what you get when you go to low temperatures. And we'll in fact see that we can theoretically show that there is a spin glass phase which is rather unusual, in the sense that it has both liquid-like degrees of freedom and glass degrees of freedom. And in fact, there is a thermodynamic phase transition which happens here. Okay, good. Right, okay, so this is in the same vein, as I said. And I mean, there are several experiments which have seen things like that. I'm just flashing some. But I mean, for example, even in this very well-studied SCGO compound, people have seen that there is this spin glass transition at a much lower temperature compared to the Curie-Weiss temperature. But even when one goes much below this putative spin glass transition temperature, local probes actually tell you that there is persistent spin dynamics going on till a very low temperature scale. So the key point in all this is that even though there is some sort of a glassy tendency, there is no sign of transition to magnetic long-range order. However, there seems to be a coexistence of both dynamical for the majority of the spins and frozen movements for sort of a smaller fraction of the spins. And there's no phase separation. So with my crude theorist understanding, that's what I can glean out of this. Okay, so right. Okay, and okay. One thing which was missed in the tutorials was the spin glass. So I just put a quick one-slide intro to it. So this is a very fast introduction because spin glasses are very non-trivial phases. So sort of the prototypical model to understand the spin glass, if you wish, maybe the Edwards-Sanderson model, where maybe you take again spins on the square lattice. If you wish, you take Ising spins. And then, instead of coupling them ferromagnetically or antiferromagnetically, you actually take certain spins and randomly couple them ferromagnetically, and the other spins you randomly couple to be antiferromagnetic. Then one can actually show that even if one goes to very low temperature, there is no phase transition to an antiferromagnet or a ferromagnet. However, there's actually a phase transition to a more non-trivial phase where the physical picture can be thought to be that the spins are actually localized. So if you go to one spin, it's sort of fluctuating, but there is an average that forms, but they're localized in random directions. So if you calculate this object, it's again 0. However, you can write more complicated order parameters to capture this. Okay, and this kind of a state actually then leads to various interesting things like very slow dynamics, and there are several other signatures. So in this talk, we can ask what happens if I take a, let's say, a theoretical model, which I know is a spin liquid at 0 disorder, okay? And then I actually put a finite amount of disorder here, and then I can ask what happens with the disorder and does anything change, okay? Right. So the case that we'll study here are Coulomb spin liquids, okay? That's a very well-known classical spin liquid. In fact, it's one of the most well-known classical spin liquids. So, so let me just give you the definition of this kind of a spin liquid. So basically, these are the ingredients that you need to construct such spin liquids. So the first ingredient is that you can see that you have some nearest neighbor or maybe next nearest neighbor interactions, which can be written like this. The sum of the spins on some elementary tetrahedron or an elementary unit and squared it. So you should be able to write the Hamiltonian in this form. So, and there are several examples where this happens, both in 2D, where this is the Kagome lattice, and in 3D, which we'll focus on in this talk, and this is the pyrochlore lattice. And there are several examples of this. And these units must share corners. So of course you can see here the triangle shear corner, here the tetrahedra shear corners, and if you draw the corresponding dual lattice, which you can just draw by putting the midpoints of these elementary units and joining them, then that dual lattice should be a bipartite lattice. So it's a bit harder to draw in 3D, but in 2D you can easily see that the dual of this Kagome lattice is the honeycomb lattice. So even though the Kagome lattice is not a bipartite lattice, but the honeycomb lattice is definitely one. Okay, so if these two conditions are satisfied, then if you go to low temperatures, you will see this very interesting spin liquid, which has algebraically decaying correlations. And if you go to momentum space, so you just Fourier transform the spin-spin correlations in real space to momentum space, then you will see these very interesting pinch point signatures in scattering as well. So this was again something which was discussed already over the past 2 days. Okay, right. So I won't be able to talk of this here because that's another talk in itself. But recently, okay, so for rotationally invariant systems for classical spins, this was believed to be the only known spin liquid. But recently we have found that there are even classical spin liquids beyond this description, and if you're interested, you can look at these papers. Okay, so in this talk, I'll instead focus on this particular example. So this is the canonical classical spin ice, if you wish, and well, there are various well-known realizations of this. One is holmium titanate, another is dysprosium titanate, and people have seen rather interesting things in experiments. For example, there's this famous experiment where Ramirez and others measured this residual spin entropy through heat capacity, and they could actually show that there is a very large residual entropy even if one goes to zero temperature. Even if one goes to very low temperature, and that's actually very close to the Pauling ice entropy. Okay. Then much more recently, using inelastic neutron scattering and certain very clever tricks, Fennell and others could show that there are indeed these pinch points which were theoretically predicted earlier. Okay. So now, much of the time when we are thinking of experiments and even talking theoretically, this is just modeled by this nearest neighbor exchange, right? And part of the reason is, if you think of it, even the nearest neighbor model gives you both this and this. Okay, so you think that's the full story. But actually, here, and this is also something which has been stressed here, here the magnetic moments of these rare earth ions are very large. They are about 10 Bohr magneton or so. And therefore, something which we know always exists between two spins. So, see, spins are after all magnetic dipoles. So, there's always a dipole-dipole interaction between spins. The reason we ignore it most of the times is because that interaction is much smaller compared to the exchange interactions. But here, because the size of the moments is large, one can actually do a calculation and just see that this term is as significant as the exchange interactions here. Okay, so here one has to consider the full story. Okay, then remarkably, if one considers the full story, if you just think of the ground state, this physics remains true. Well, I have to slightly tweak this model and then I can show that this physics remains true. However, if you think of the finite temperature physics, you can actually show that there are already signatures of the fact that the spins have long-range interactions. So that's point number one, which I'll hope to stress during this talk. Point number two is, if you put disorder here, I talked about this thermodynamic phase transition and then the system going into a unusual glass phase. If you ignore this term, then there would not be this glass phase. Okay, so, but of course this term is there, right? And we even know the sizes of these couplings, etc., etc. So if you can solve the full theory, of course, you will just solve the full theory. And I'll just show you the answers. Okay. Oh, but before that, I have to do some, I have to just set up the stage for this slightly modified Hamiltonian. This Hamiltonian is still a bit too difficult to solve, and it's also hard to imagine things in one's head. But there's a very nice representation due to Castelnuovo, Moisner, and Sondi, and they did this work in 2008, due to which there was a lot of actually, there was this paper was very important in the field because not only did it provide a simple way of looking at a complicated problem, it actually gave rise to many further insights. And it's actually a very simple realization. So let's actually see what they did. So what they did was to write this complicated long-range problem of spins in terms of some charge degrees of freedom. Okay, so how do you do that? So as I already said, a spin is like a magnetic dipole, right? So this is something that we have also learned in school, that suppose you have a magnetic dipole, the way to cheat and think about it is that you just represent it by a dumbbell. And so there are two charges, so this is opposite this, and basically charge times the distance is your dipole moment, right? Now, of course, this is an approximate description, and this description will fail if you probe the magnetic field of a dipole at the scale of this separation. But if you are probing at any scale which is reasonably large compared to the separation, this is a perfectly valid description. So they just used this idea. So what they did was the following. So, oh, and I forgot to point out here, there was one thing I should have pointed out. So see, each of these spin variables, this is not a Heisenberg degree of freedom here. This is in fact an Ising degree of freedom. But the Ising spins, they actually have their easy axis along these particular 4 directions. So you take any tetrahedron, you mark the center of it, and you just draw lines out of it. Then the Ising spins actually like to point like this, out or in, and so on and so forth. Okay, right. So now you take this problem of spins, and then you go to the dual lattice of the pyrochlore lattice. So the dual lattice of the pyrochlore lattice is this diamond lattice, right? So each spin lives on the center of this bond, right? So you take any bond, there's a spin living here, there's a spin living here, here, and so on. And this is, of course, a bipartite lattice, okay? Right. So now what you do is, you know the lattice spacing of this dual lattice. Let's call this A sub D. Then as we know the moment size, we automatically know the quote-unquote magnetic charge sitting here, right? So suppose I have this configuration where, let's say, this spin is pointing out, this spin is pointing it, so on and so forth. Then all I do is just represent them by a sort of a dipole here, where this is, let's say, the plus charge and this blue is the minus charge. For this guy, therefore, this blue is the minus charge and this red is the plus charge, so on and so forth, right? Good. Then what's the use of this picture? The nice thing about this picture is then there is a very simple way of thinking of this dipolar interaction. So the way to think about it is the following. I mean, suppose you have a bunch of charges, some of them may be positive, some of them may be negative. I mean, if you just set up a multipole expansion, and if your system is basically charge neutral, you will immediately see that the first non-trivial term that you generate are dipole-dipole interactions like this. So this automatically comes out if you just think of the interactions of these charges, right? Just by doing a multipole expansion, okay? Secondly, you see the constant here. The constant. So this is, of course, your Coulomb's law. And this constant is just the usual permeability between 2 magnetic charges in vacuum, right? And this constant is the same here because, after all, this is the physical dipole-dipole interaction between spins. And therefore, this is actually being generated by this Coulomb interaction. So that's another way of thinking about it, right? Okay. So then the next thing to look at is, this is the interaction when this charge is sitting here and maybe that charge is sitting here. Another thing to note is that, of course, at this point, there are 4 charges here. So you can just superpose them and take the total charge here. You can do the same here, here, and so on. Now, you can actually show that for writing this Hamiltonian, you don't need any on-site charge interaction. Of course, if you write an on-site charge interaction, this term will just blow up. Rather, you just need to put a sort of a chemical potential here, and you can work out what this V naught is just by putting the constraint that you want the nearest neighbor magnetic interactions to be correctly reproduced. Okay, so that's how all this is done. It's, in hindsight, none of it is very hard. But of course, when they realized it, it was very cool. Right. Okay. So we have converted a problem of spins into another problem of charges which live on this dual lattice. And there is this Coulomb interaction between them whenever the charges are on 2 different sides. And there is an on-site term, which, if you wish, is like a chemical potential. Now, you can easily see that if this V naught is sufficiently high compared to this scale, mu naught by 4 pi, then the ground state of this problem is that each Q alpha is 0, right? That's the ground state of this problem. Now, that just means that you go to each tetrahedron and you have 2 in spins and 2 out spins. That's the meaning of this, right? And you can furthermore show that, for example, you could do a simulation or try to do some rough back-of-the-envelope calculations, but some people actually did the hard simulations. You can actually show that if you keep decreasing, 1 minute, if you keep decreasing V naught, ultimately there's a phase transition to some other kind of a ground state where these Q alphas are not all 0, but thankfully, all these spinized compounds that I talked about, they actually lie on the other side, where you are in the simple ground state manifold, which is also the ground state manifold of the nearest neighbor model. So this explains why this long-range model and this slightly tweaked model have identical ground states to the short range model. Okay, so that's point one. Now I'll go to the finite temperature physics of it. But yeah, you had it. Yeah, that's what I said. Right. That's exactly what I said. Right. Because if you think V0 is sufficiently high, that's the ground state. Right. Okay. So far, so good. This is the ground state. Now let's. Let me just give you the result before I go on to each of the aspects here. So now, let's put a finite amount of non-magnetic disorder on this lattice. So you just pick up some sides. Let's say you pick a fraction x of sides, and you just throw non-magnetic disorder at random, right? So wherever there is a non-magnetic disorder in your original Hamiltonian, you just switch off the Ising variable. That's it. So that's your new Hamiltonian. But this is, of course, a random problem now. So in the limit, when x is small, we can do a controlled theoretical calculation. But even if x is sort of moderately large, many of the things I expect would go through. Of course, what is moderately large is always subjective. But okay, so let's go on. So if x is 0, then of course we know the phase diagram here. There is a certain temperature scale, which in terms of the sort of the more basic parameters of the Dumbbell model are this. And this temperature scale gives you the cost of producing a monopole, basically. Okay, so a monopole in the spin language is nothing but when you break this 2 in 2 out constraint. In the charge language, that would mean that there's actually a charge sitting on some side of the dual diamond lattice, right? Okay. So basically, if you go below this, then you are dominated by some physics where you have these pinch points, and you can even calculate what happens to the pinch point at finite temperature by noting down the concentration of these monopoles. So these monopoles at low temperature just behave like a gas of plus and minus charges, which interact through Debye-Huckel screening. That's basically the physics here. Okay, right. Now let's say we put in disorders. So there's a finite x now. Okay, then there are various crossovers and phase transitions which take place. Okay, so just for concreteness, I have put some numbers here. So let's take x to be 0.1, and let's say I take the holmium titanate parameters. Okay, so of course you can sort of analytically work out what these crossover scales are, but just for illustration, I've put these numbers here. So see, one thing is when you put these impurities, then around the impurity, it becomes especially easy to create a monopole. So I would distinguish the bulk monopoles from these impurity monopoles, which have a much lesser energy cost to produce. Okay, right. So then, if you go below this crossover temperature scale T delta, then actually, if you calculate the total monopole concentration in your system, then these impurity monopoles in fact dominate over the free monopoles, okay? And that of course changes the correlation, the way the correlation functions behave in your system, and it also has some implications about the dynamics in these spinized material. Because one very simple way of tuning the monopole concentration here, which is independent of temperature, is to just tune this X, okay? Secondly, there is this continuous phase transition. This is a thermodynamic phase transition at this Tc. So at this concentration, this number is 0.11 Kelvin, below which the system actually no longer stays a spin liquid. It in fact goes into a spin glass phase. But this spin glass phase has certain degrees of freedom, which we'll soon identify. These will be some 6 spin degrees of freedom. So these 6 spin degrees of freedom actually freeze into a glass, and that gives you a thermodynamic transition, whereas the rest of the bulk keeps on fluctuating, okay? Ultimately, so that's the meaning of this fluctuating bulk here. Ultimately, as you keep lowering the temperature, there's an interesting sort of an interplay between these liquid degrees of freedom and these glass degrees of freedom, and there is some crossover physics which actually freezes the entire bulk, okay? So that's the physical picture here. That's what happens if you put disorder in this problem, okay? right? And if you just work out everything, these are the scales, the various crossover scales and the phase transition scale, if you just work out from this Dumbbell model. And here I would like to mention that recently there have been some studies on this particular spinized material where this X is not terribly small, therefore I won't like to say that this is exactly what I'm saying, but nonetheless in these experiments they show some sharp signatures of both some liquid-like degrees of freedom and some glass-like degrees of freedom. Okay, but as I said, I mean, there is still a long way to go from here to here. I mean, this modeling, I don't know. Okay, good. So now let me be slightly quick and show you the results. Yasir, how much time do I have? Okay. 10 plus 5 you mean? Okay, yes, right. Okay, good. So let me tell you now the physics and not go into too much explanation. If you're interested, I can always talk later about any of the points. So the first thing is about these pinch points. So at zero temperature, when we are in this ice manifold of 2 in 2 out states, then it's well known that there are these pinch points in S of Q, right? And the pinch point is nothing but a discontinuous singularity in this spin structure factor, right? Now, what happens when there is long range? When there is long range, it's very easy to convince yourself that at high temperature, the pinch points would survive. That's very straightforward. Of course, they'll survive, but they'll be rather weak. So suppose at zero temperature, you go in this direction in momentum space and you go in that direction. This, by the way, is called antinodal line. Oh, sorry. This is called the antinodal line and this is called the nodal line. Because at zero temperature, you can show that if you're in the ice manifold, there's no scattering here. And here there is maximum scattering. That's why the names, okay? So at zero temperature, the jump, let's say, is 1 in some units. So that's your maximum jump. Then if you go to very high temperature, the size of the jump keeps reducing. And of course, at infinite temperature, it has to go to 0. But at any finite temperature, there's a jump. And the way to see it is, you had this Hamiltonian. You can just take that Hamiltonian and do a high temperature expansion of the spin-spin correlation function. Now, the leading term of a high temperature expansion is just Jij divided by temperature, right? But here Jij is a long-range function, right? It's a long-range function. And it's this function. Now, if you Fourier transform this function, you'll again get back pinch points because, I mean, that's a mathematical fact. That's it, right? So, okay. So therefore, there are pinch points even at very high temperature, right? And yeah, this is actually some experiment on holmium titanate, but it was doped slightly with yttrium, and that's non-magnetic, okay? And this is a comparison of, oh, now I forgot. This is the high temperature data from our theory, and the theory is nothing sophisticated, it's just high temperature expansion, and this is what the experiments see, okay? Good. Now, the more interesting question, which is much more non-trivial, is what happens at low temperature. Of course, you can't push this trick of high temperature to low temperature because you have to go to a huge number of order in a perturbation theory. But there's a different way of doing, gleaning out the physics at low temperature. That's quite involved. I won't have time to go into that, but this is this paper. So you can show two central things. First is that the pinch point still survives. So if you have a nearest neighbor model, all that would happen at low temperature is if you heat up the system to some non-zero temperature, then this pinch point broadens. But here, in the presence of long range, actually, if you zoom in, you will see something like this. So what happens really is, if you just take cuts like this, the pinch point just vanishes at any finite temperature for a nearest neighbor model. But for a long-range model, it's like this. And there is a certain width of this thing at finite temperature. So this width goes like this, okay? So this width just depends on this ratio d by t in a particular manner, and it depends on the monopole concentration, right? So this rho is the monopole concentration, okay. Secondly, there is a discontinuity. You can clearly see that there is a discontinuity here, like so, in the long-range model. And this also is related to this precise ratio, but the rho does not appear here. Okay, so that's this functional form. Good. In fact, in this paper, we have an analytic form. Of course, that's an approximate theory. We have an analytic form for the full spin-spin correlations. And with Wojciech-Kaiser, I did some numerics, which we never published. I don't know why, but okay. Well, part of the reason is he moved to biology. Okay, right. Where we can just take our analytic solution, and Wojciech did some very nice numerics on the actual long-range model. And basically, the line here is the analytic solution, and the dots are the numerics. And actually, in this analytic thing, there is no fitting parameter. Everything can be self-consistently determined. Okay, so, right, good. So one key point is that there are these pinch points even at finite temperature. Now, what happens if you put in disorder? So if you put in disorder, so let's say you're in the low X limit. So your disorder is, the fraction of disordered size is small. Then the leading behavior is to consider tetrahedra like this, right? So now if you knock off one spin from, let's say this side, then you can immediately see that if you go to very low temperature, there is no way to satisfy ice rule here and ice rule here, because there are 3 spins here and 3 spins here. So you cannot add them up to be 0. So all that you can form is an extended dipole like this, or an extended charge to object like this, in terms of this Dumbbell model, right? Secondly, what you can just calculate is the cost of creating this impurity monopole. I call this an impurity monopole because, of course, in the bulk, this is not a missing spin, right? So this impurity monopole has a lower cost of creation than a bulk monopole, and due to that, and you can just work it out, if you go below a certain temperature scale, actually the number of these impurity monopoles will take over the bulk monopoles, right? And of course, you have to use the full density. And we have shown this, again, this is something I have not published. You can actually do the calculation even for the disordered problem. Nothing changes here. All you need to put here is the renormalized rho, and that's it. So even with a small amount of impurity, this result does not change. The jump will still be the same. It's not sensitive to X. Whereas this will change because your rho will increase, and you can actually, if you wish, probe that. Okay, good. Right. Now, we go to the, in whatever time I have left, to the spin class phase, even at even lower temperature. So let me just try to show it to you in pictures, the basic physics. So suppose you knock out some sites here, right? So as I said, around these knocked out sites, you can either form a dipolar object or a charged 2 object. Now, there is a certain, so the dipolar object is lower in energy compared to the charged 2 object around these sites. So if you go below this scale of creating these charged objects, which is delta here, then, of course, you just consider the dipoles, right, to leading order. And then everything else sums up to 0 charge here, right? So the most basic picture is that you just have these effective dipoles sitting here. Now, where do these effective dipoles come out? So see, if you knock out a spin here, let's say everything followed ice rule here and here. If you knock out this spin here, you see that you have 6 spins left here. If you just sum up these 6 spins, you will form an effective dipole or a magnetic moment, which is exactly opposite to the spin that you knocked out. So this is like a ghost spin, or if you want, this is like the magnetic version of a hole in an almost filled band, right? So then you're just left with this problem of ghost spins. And then there is this background. So what is this background? This background is, see, of course, these charge degrees of freedom here are all 0, but the spins are fluctuating a lot, right? Because there's a lot of ways in which you can form loops here, and that's your spin liquid dynamics. So you can actually integrate out all of that, and you can show what that leads to, and that leads to another effective interaction between these dipoles. So these dipoles, as I said, are these 6-spin objects, and that's this interaction between the ghost spins, right? And so it has this usual D part. This D part comes because this is a dipole and this is a dipole, so it should have this interaction. But there's also this renormalized part due to the background spin liquid. Okay, so this is the full story. And you can numerically show that this is exactly the case, right? So see, we have mapped from this problem where there were only a few number of missing sites to a much simpler problem where there are only a few number of random spins, and that's it. So this is a much simpler problem than this, right? Okay. Now, it turns out that it is still very hard to show that this random problem of spins with dipole interactions has a glass transition. So this is where Tushar's work comes in, and so I'm skipping some of the slides. So basically, you can, okay, this is some slide I showed in my overview talk. So one way of simulating spin glasses normally is you can do something called parallel tempering in temperature and try to fasten the dynamics and relax a complicated problem like a spin glass. Now, this works reasonably well if you have short-range interactions, but for these kinds of long-range interacting problems, you can show that this miserably fails. So then we needed to devise a cluster algorithm where basically this snapshot shows that, okay, this snapshot and its color coding shows that if you have a darker color, that means that two co-spins are interacting with a stronger Jij. If there is a lighter color, that means that there is a weaker Jij. So you see, because there are these power law interactions, there is a huge hierarchy of possible interactions. But there is a way to devise a cluster algorithm which actually takes care of all that, and that actually works much better than any conventional algorithm. Just to prove that point, and I'll just take 2 more minutes, just to prove that point, basically, if you calculate what is called the autocorrelation time of any dynamics, you should know that this is the log scale, and this is like the number of ghost spins. Then you see, this is how the conventional algorithm performs. You can see that the time scale is really rapidly diverging, right, for growing number of spins, whereas for this cluster algorithm is much below this, right? So we could actually use that, and we could then do some nice scaling and show that there is indeed a continuous phase transition in this problem to this interesting topological spin glass phase, which has these 6 spin degrees of objects which are frozen, and the rest is fluctuating. And the last point I would like to mention is that it's actually also very interesting to look at the dynamical response of this phase. Now, suppose you're not at TC, but let's say at some temperature which is significantly higher than TC. Even then, because this is a long-range interacting system, if you just look at the autocorrelation functions of individual spins here, you will see that there's a huge hierarchy of time scales. Basically, some of these ghost spins fluctuate very slowly, some fluctuate faster, some fluctuate even faster. So this is basically called a dynamical Griffiths effect. So it's been known for short-range classes that something like this happens, but the key difference here is that this is a long-range system, and therefore, this is a much more dramatic effect. So just to give you an example, even if you are at 4 times TC, which is much higher than the critical temperature, you would still see this effect very strongly, right? So this is another way of probing such things. Yeah, just a sec. Anyway, my talk is over. Just 1 second. Right, so good. So this is the conclusion of my talk. And basically, now we are working on some examples of trying to generalize this thing to quantum spin liquids, and we think that we can work out this thing in some examples where there are these interesting low temperature disordered phases even there, and this is the thing here, and thanks for your attention. Yeah.
So the floor is now open for questions.
So of course, this cluster algorithm is very impressive from a theoretical point of view, but if I want to model a real material with this, isn't the single spin flip algorithm a more accurate?
Oh, sorry. Thanks for this question. When I showed this graph, this is a local algorithm.
Right.
Yeah, so this is a local algorithm.
If you go back to the previous one where you were showing this time scale getting...
Yeah.
So as a function of temperature, what is the behavior at that freezing? I mean, there is those 6 spin degrees of freedom freeze.
This is a difficult question because you see, I mean, even if we are at some very moderate system size, this time scale diverges so rapidly we cannot even get equilibrated data.
No, that's right. But I mean, so it's basically, is there a Vogel-Fulker kind of law?
I haven't been able to estimate that well enough because I cannot fit things
at a non-zero temperature.
I know.
Okay,
but I mean, it's just hard to fit it like that.
Okay.
That's why we invented this cluster thing to at least first understand the equilibrium phase diagram.
Yes.
Then I'm saying that, of course, the dynamics is also extremely interesting.
Yes.
So here, when you've looked at disorder, it's always like intrinsic disorder, right, where the Hamiltonian itself has some. Have you thought about doing this with like quench disorder? Like,
Oh, so this is quench disorder, by the way.
okay, so this last one is, so there is, the Hamiltonian is still has all the symmetries and you're just.
Exactly. You're just knocking off some sides.
Okay.
Well, of course, you're breaking then translation symmetry because you're knocking off some sides.
Oh, I guess maybe by.
But these are quench disorder. This is not moving around.
No, I guess what I meant by is like getting disorder just by dropping the temperature, like by doing a quench in a system without any disorder in it, and just relying on the fact that you're going from a high temperature to.
Oh, I see. So as I said, if I put x equal to 0 here, I can prove that there is no spin glass.
Okay.
Yes, that's the short answer.
Okay, well, thank you.
Sorry, I missed the point probably. The charge to monopoles, what do they do in the system? So,
Oh, okay. Yeah. So, well, they do several things, but to a theorist, the first thing they do is generate a correlation length. So this is something I did not mention because, as always, I'm managing my time horribly. Oh God, sorry. Here. So you see, so if you heat up the system, there's this finite width in momentum space. You can ask, what does it mean in real space? So let me just tell you the answer shortly in a very quick manner. So suppose you draw the spin-spin correlation function in real space on a log-log scale. So this is a log-log scale. At a finite temperature, you will initially see that there is an exponential decay. And the scale of that is set by the density of these monopoles. And then, beyond this correlation length, it'll actually give you an algebraic power law tail. And that's why the pinch point survives here. So initially, it's an exponential decay, and then it's a power law decay at finite temperature.
Any further comments, questions?
So you had two kinds of monopoles, right? These impurity and the topological.
No, impurity and bulk.
And sorry, just the violations of the constraint, right?
Yeah, of course.
So those second kind of monopoles only play a role in the liquid phase. Is that the point? And in this glass phase, these.
Oh, okay. See, in the glass phase, the temperature is anyway small enough. See, if this x is small, where is that? Yeah. If this x is small, then there is a huge separation between these scales, right? Then if you go in the glass phase anyway, you can, to a very good approximation, forget the monopoles generated. You can think about the dipoles, and you can average out all the other spin fluctuations with that effective term that I wrote down.
And can you also forget the impurity monopoles on the other side?
No, of course not. No. In fact, as I showed, of course, if you are at here, if you're below this temperature scale, which I can calculate, then in fact the number of these impurity monopoles dominates over the bulk monopoles. So if you just do a bulk calculation and forget the impurity ones, you'll just get a wrong answer. Yeah.
Okay, then in the interest of time, let's push all further discussion to the lunch and afterwards. So let's thank Dr. Arnab Sen again for a wonderful talk. And,